As you know, this week is going to be a makeup week for the labs. So if you are running behind on any of the labs, or if you have any questions related to the course or any homeworks, please feel free to reach out to your TA. They'll be available this week. It's kind of considered it as a makeup week if you have missed something over the last few weeks. Okay, and we are going to continue with our lab number 6 starting next week. I have also uploaded the solutions to your homework 4 and homework 5, and most of you have done pretty well in your homework 4 and 5. I'll also grade and upload the grades for your exam number 2 by the end of this week. One other announcement is that there's another homework posted, homework 6, that will be due in a week. I'll show what that homework contains. But before that, so till now, what we are discussing is MOSFET. And we have looked.
Ok, rồi nói đi muốn cái gì hả đồ ba gai.
So people on Zoom, could you please mute? All right, thank you. So till now we have discussed about MOSFET-based circuits, but we have mostly looked into single MOSFET circuits, right? So you have looked into a common source amplifier or a common drain amplifier, common gate amplifiers, and so on. You also had multi-stage amplifiers, which were part of your homework number 5, basically. Let's see. So in your homework number 5, you have looked into multi-stage amplifiers, where, for example, you had a common source stage with source degeneration as your first stage. And then you had your second stage, which was a source follower or a common drain. And you know that for multi-stage amplifiers, it's the concept of cascading, that you have one amplifier followed by another amplifier. So if the first amplifier has a gain of A1 and the second amplifier has a gain of A2, the total amount of gain for this cascade of amplifiers is going to be A1 multiplied with A2. So you have looked into cascade of or multi-stage amplifiers still containing a single MOSFET per amplifier. So for example, on the first stage, you had this amplifier, and on the second stage, you had this. But as you know that most of the modern circuits contain thousands of MOSFETs. If you're looking into digital circuits, they might even contain millions of MOSFETs. So now we are going to learn a little bit about how do we analyze if there are multiple MOSFETs in the same circuit. Okay? So one of the topologies that we are going to discuss about today is called current mirror. And we are going to talk about why it is called current mirror, what is the functionality, and so on. But before that, in your homework number 6, let's open this once more. But I think I have it opened over here. So in your homework number 6, there are 2 problems. The first one is something that we talked about in the class a little bit, that the small signal model for the MOSFET. So for example, this is the MOSFET that you have in this particular circuit. And again, this is going to be pretty simple if you do the small signal analysis. The only catch here in this first problem is that your small signal analysis looks little different from what you have learned till now. And why does it look different? That's because you have this CGS, a gate to source capacitance between the gate and the source of the MOSFET. Everything else is same. So earlier, the model that you had learned in class is basically you have your gate terminal, you have your source terminal, and it's an open circuit between your gate and source, right? And then on the drain side, you have this current source, which is GM times VGS. And then, of course, you can consider RO if lambda is given, and RO is going to be 1 over lambda ID. But this is what you had learned over the last few weeks in the class, right? And you have applied this particular small signal model to solve different kinds of problems. Now, for homework 6, the only difference is that you are being given a gate to source capacitance. Now, why is this important? We talked about this a little bit in the last lecture or the lecture before that every terminal in a MOSFET will have some parasitic capacitance associated with it. So if I take this MOSFET over here, there would be a parasitic capacitance between the gate and the source terminal. There would also be a parasitic capacitance between gate and drain terminal, and so on. So in this case, we are only considering the parasitic capacitance between the gate and source terminal. But what does that mean? That means that if you are looking into the gate, at DC frequencies, you'll still see an infinite impedance, right? Because at DC, this capacitor is open. Remember that the impedance of a capacitor is 1 upon j omega c, where omega is the angular frequency, which means that when omega is equal to 0, that is at DC, you have infinite impedance for the capacitor. But for AC frequencies, for high enough frequencies, when omega is very high, your denominator becomes very high, which means that the impedance becomes very small, which is as good as a short, right? So if your omega is infinitely large, or if your capacitance is infinitely large, then your impedance becomes almost equal to 0. That means there is a short between gate and source. And in that case, even though the gate itself, so there is a silicon dioxide at the gate, right? So even though there is no current flow through that silicon dioxide, there could be AC current flow through this capacitance, because the capacitance becomes a short between the gate and the source. That can happen at high enough frequencies. And that's why I wanted to introduce this concept of parasitic capacitances in this homework. Again, it depends on what frequency you operate at. If you're at kilohertz frequencies, maybe even at lower megahertz frequencies, it doesn't matter, right? The capacitance, the impedance of the capacitor is very small. Let's just take an example that, okay, let's say my capacitance is 1 picofarad, which is pretty large. You need to consider that if you are implementing this MOSFET as part of a silicon ASIC and application-specific IC, then the capacitance looking at the gate is generally in the range of tens of femtofarad, or even lower in certain technology. So 1 picofarad is pretty high. Now, if your omega is 1 megarads per second, 1 megaradians per second, and I'm the unit for omega, I'm writing that down as radians per second, because this is angular frequency. You know that omega is equal to 2 pi times f, where f can be given in terms of hertz, but 2 pi times that whatever frequency you're given, that gives you the angular frequency. Let's say omega is 1 mega and capacitance is 1 pico. So you have 1 mega multiplied with 1 pico. So 1 mega is 10 to the power 6 and 1 pico is 10 to the power minus 12. So if you multiply those two in the denominator, and you are trying to find out the absolute value of the impedance, 1 upon j omega c, so you still have 10 to the power minus 6 in the denominator, right? Because 10 to the power 6 multiplied with 10 to the power minus 12 still gives you 10 to the power minus 6. So you have 10 to the power minus 6 in the denominator. That means 1 upon 10 to the power minus 6, or a 1 mega ohm of impedance, is something that we'll see for that capacitance of 1 picofarad. Now, in most cases, this capacitance will be much, much lower than 1 picofarad. A transistor generally has only a few femtofarads of gate to source capacitance. So in that case, you are looking at an impedance which is ranging toward like tens of mega ohms to even a giga ohm. So that impedance is generally high, even at megahertz frequency. But if you go to gigahertz frequency, then of course this 10 to the power 6 will become 10 to the power 9. And then this will become 10 to the power this will stay 10 to the power minus 12. So the multiplication of those two will still give you 10 to the power minus 3. And that means that this impedance will be in the range of kilo ohms. That's something you can consider as pretty small. And then if you're looking at tens of gigahertz frequencies, which is true for many RF or millimeter wave circuits, then you know that this impedance is going to be in ohms. And that means that there is a very low impedance path through this capacitance from the gate to the source, even though the gate itself has a dioxide, silicon dioxide. Okay. So I wanted to introduce this concept through this homework, that at high enough frequencies, you might see the effect of this capacitance. So what you are asked to do is just find out the small signal AC equivalent impedance. So basically the impedance looking here, if you're considering a capacitance between your gate and source. So the method should be very simple. As you have learned, just find out the Thevenin equivalent resistance, looking into the input, looking into the left side of this RG resistance. Of course, you'll get rid of any independent voltage source in that case, and then you'll try to find out what would be the AC equivalent resistance looking into the input. Just consider that there is a capacitance between gate and source to solve this problem. Question? Right, or Thevenin equivalent impedance. Let's call it Thevenin equivalent impedance now, because you have a capacitance component. Yeah.
After we figure out the capacitor, do we combine it in series and then parallel with the impedance of the.
Yeah, so impedance generally comes in, let's say, if it is series, you just add the impedances. If it is in parallel, you take the parallel combination of impedances. Right? If they're on the path, then yes, right? But of course, you're looking into the impedance looking here, right? So the impedances that you'll see is, of course, the impedance of the capacitor. You'll also see the impedance of this capacitor CS. So at the source terminal, there would be another capacitance connected. So you'll see the impedance of that capacitor as well. So let's say 1 upon SCS, right? And here you'll be seeing 1 upon SCGS. That's the impedance of the gate to source capacitance. And on the drain side, of course, you're connecting this node to ground because you have VDD over here. And on the gate, you also have RG. So you have a resistance RG. And so basically, if you look at the current flow, there is one current flowing through this path, and there is one current flowing in through this path. You add those two currents because KCL will inherently add those two currents. And then the total amount of current coming from the left and coming from the right, that will flow through this 1 upon SCS impedance. Just solve that, and then you'll see what would be the effective impedance looking from the left side. So what would be the impedance of the current source? There is no series resistance of a current source. You already know that, right? There could be a parallel resistance of the current source, which is the RO of the transistor itself, right? But in this case, RO is not given, or you can ignore RO because you're asked to use the small signal model which does not contain RO. So, okay, I didn't get the question. So what impedance you want to ground?
Because the current
Correct. No, current source is not a short. Voltage source is a short, right? So current source does not have, so there is no impedance associated with this ideal current source. Only if this is a non-ideal current source, you'll see a resistance in parallel to that. But there is no series, even if it is an ideal current source or a non-ideal current source, there is no impedance of a current source. In series, there's no series impedance of a current source, whether it's ideal or non-ideal, it doesn't matter. There's only if it is non-ideal, you have a parallel impedance of a current source, but never a series impedance.
But it doesn't connect to ground.
It cannot be connected to ground because your source node is connected to a capacitor and then to ground. Right. Okay. All right. So that's the first question. The second question is something that we are talking about that, okay, so now that we know that we can have multiple transistors in your circuit. So let's say you're given a circuit that looks like this. I'll also post a similar problem, which will help you to solve this problem number 2. So I haven't posted it yet in Canvas, but I'll post a similar problem that will help you to find out what is going to be the overall voltage gain. You're asked to find out the low frequency small signal output voltage. That is basically this V out, right? So you're asked to find out what is the output voltage, the small signal overall output voltage, as a function of the input current. So there is an input current coming in over here. So you know that this is the input AC current, and you'll generate a AC voltage at the output. So what kind of an amplifier is this? Because it has output voltage and an input current. So the transfer function is voltage over current, which is an impedance. So that means this is a transimpedance amplifier. Okay. So you're asked to find out how this input current gets converted into voltage. Now again, I'll post a similar problem that will help you to solve this problem number 2. But the basic approach should be you want to do a divide and conquer. You want to figure out in this big circuit, you see that there are multiple transistors over here, and it looks like a very complicated circuit when you look at it at first. But if you look at it closely, you'll see that you already know certain components in this circuit. For example, if you look at the input side, just look at, let's say, this stage. So you already know this component that, okay, I have a transistor, I have a MOSFET here, my input is provided at the source, my output is taken from the drain. and my gate is biased. So see, I have a V bias 1 at my gate, which means that the gate is an AC ground or a reference point. So this is your common gate amplifier. Right? So you already know the components in this big circuit. So do a divide and conquer, find out what are the known components. For example, this component is a common gate amplifier. And for that common gate amplifier, one interesting thing that you need to keep in mind, that what do you know about the gain of the common gate amplifier is that the gain is plus GM times RO, or GM times, let's say, R out, whatever R out you have. Now GM is the GM for this transistor. R out is the output resistance that you see at the output node, which is over here. So what is the output resistance that you see at this node? You see a resistance R1 looking up. You see an infinite resistance looking into the drain of the transistor, because you generally see a resistance of RO. This is something we proved in the last few lectures, that looking into the drain of the transistor, you'll see RO. Looking into the source of the transistor, you'll see 1 upon GM. Again, you can prove this yourself by doing a AC equivalent Thevenin model, by drawing the Thevenin equivalent model of the transistor, and then finding out what is the resistance at the drain or the resistance at the source. The resistance at the source will be 1 upon GM. The resistance looking into the drain will be RO. So because in the problem, you'll see that, so all the ROs are given to be infinitely large. All the GMs are given to be equal. GM of transistor 1, transistor 2, 3, 4, 5, all of them are given to be equal, let's say GM. And then the resistors, the physical resistors that are present, R1, R2, R1, R4, and R3, they are given to be 1 upon GM. So all the resistors are given to be 1 upon GM. All the GMs are given to be equal. And all the ROs are given to be infinite. That means the lambda is 0. So that makes the problem a little simpler than what you will actually have in a realistic circuit. But then still, it's still quite complex because you have multiple stages. So how do you solve it? Of course, you divide and conquer. You first find out what is my first stage. My first stage is this one, which is a common gate. And again, the gain for the common gate stage, I'm not going to prove it again because we did that 2 lectures back. Please go back to that discussion if you want to know the proof of the gain for the common gate amplifier. Now, remember that this is voltage gain. This is basically voltage gain for common gate amplifier. Since in this case, your input is a current, in this case, your input is a current, you're converting your current into a voltage. This input current will come in, and then it will see 2 paths, one path going down and one path going up. Which path will it take? Or would there be a current division? It will only take the path going up. Why is that? Because as you know that a current source, an ideal current source, has infinite impedance. Right? Ideal voltage source has 0 series resistance associated with it. Ideal current source has infinite impedance associated with it. Again, E-circuits or circuits 101 concept. Right? That any current source means infinite impedance. Any voltage source means 0 impedance. So when this current is coming in, it will see 2 paths. One path that the current can go down, and another path where the current can go up. Because the current sees an infinite resistance going down, looking down, the current will not take that path at all. So the path going down will not be taken at all by the input current. The entire input current will go up through the source of the transistor. Because at the source of the transistor, you see 1 upon GM. If you see 2 resistances, one resistance is 1 upon GM, and then there is another parallel resistance, which is infinite. Which path will the current take if you're pushing in a current at this node? The current will always flow through the 1 upon GM resistance. The entire current will flow through the 1 upon GM resistance, and the current will never flow through the infinite resistance. Questions?
Wait, why is it infinite again?
So what is the impedance of a current source? So if you have a current source, let's say an ideal current source. What is the impedance of an ideal current source? Infinity. That's why the resistance is infinity, right? It's as simple as that. Okay. And if you see a voltage source, the impedance of a voltage source is 0. right? Because voltage sources, remember that when you do the Thevenin equivalence, you short the voltage sources and open the current sources.
Yeah,
So why is that? Because the current source is an infinite impedance, which is an open.
but that's only for independent, not.
Right, that's right. All right, so that is the reason why this entire current will go through the source of the transistor and will flow up. Right? Again, could be a very complex concept to understand at first, but if you think about it, it's actually very simple. Current cannot flow through an infinite resistance. It will always take the other path, which is 1 upon GM resistance. Looking into the source of this transistor, you see 1 upon GM. So all this current, all the input current will go up, and then whatever is the output resistance at this node, at the drain node, the current will be multiplied with the resistance and give you the voltage. That's Ohm's law. Current gets multiplied with the resistance, gives you voltage, that's Ohm's law. So all the current goes up, all the current is at the drain node. Whatever resistance you have at the drain node, multiply that with the current, you'll get the voltage. So if I now want to write out, so because we have found out the voltage gain equation for common gate as GM times R out, don't directly apply that because that's a voltage gain equation. In this case, you have a current input. So always try to follow that where would that current will go if you have a circuit like this, right? So the voltage gain formula is not applicable here because your input is a current. But if you follow the path of the current, all the current goes up to the drain node. So now if you multiply the resistance at the drain node with the current, you'll get the voltage at the drain node through Ohm's law. Okay. So what is the resistance at the drain node? Again, looking up, you see R1. Looking down, you'll see infinite. Looking towards right, what would you see? Looking towards the right, you see the gate of this transistor. So that's infinite. Okay. But you also have another path. And that path, let me just clear this. That path actually goes to the source of another transistor. So what is the effective resistance that you see at this node? You see R1. In parallel with R1, you'll have infinite resistance, which is basically the resistance looking into the drain of this transistor. Then on the right side, you see another infinite resistance, which is the gate of the transistor M2. And then in parallel to all of that, you'll see the resistance looking into the source terminal of M3, which is 1 upon GM. So effectively, you have R1 in parallel with 1 upon GM. Now in the problem, it is given that the value of the R1 is also equal to 1 upon GM. So you have 1 upon GM in parallel with 1 upon GM. So you have 1 upon twice GM. And that is only because your R1 is equal to 1 upon GM. That's given in the problem. It's not an absolute truth. So this is not a categorical truth. So this is given in the problem that consider the physical resistances as equal to 1 upon GM. So that's why the resistance looked at the drain terminal is going to be 1 upon twice GM. So that's the resistance looking into the drain terminal of the first stage. So what is going to be the voltage at the drain terminal over here? The voltage is going to be equal to I in, which is the input current, multiplied with the resistance, which is 1 upon twice GM. So I in divided by twice GM is going to be the voltage at this terminal. And from that point onwards, you can just consider the voltage because you have already converted the input current into a voltage at the output of the first stage. And then all of these stages, you can consider them as voltage amplifiers because input is voltage, output is also voltage. Because finally, you want to find out a voltage output. So, yes.
Oh, so is the gate, are we doing that weird thing with like V out? Like, because gates usually V out, V in, or I out, I in.
So again, gain can be if the gain is voltage gain, that's V out over V in. If it is current gain, it's I out over I in. If it is transimpedance gain, it's V out over I in. And if it is transconductance gain, it's I out over V in. So gain can be any of these four, right? So in this case, you converted your input current into a voltage at the output of the first stage, and that is equal to I in divided by twice GM. Okay, so that's the voltage at this terminal. Now let me clear this up. So you know that the voltage at this terminal is going to be I in divided by twice Gm. Now from that point onwards, everything will be very easy, because over here, as you see that this stage is a source follower stage. Why is this a source follower? Your input is at the gate, your output is taken from the source, and your drain terminal is connected to VDD, which is an AC ground. So this is a common drain or a source follower stage. The gain of a source follower is almost equal to 1. Or if you want to be exact, then the gain of a source follower is, you already know that GMRS divided by 1 plus GMRS. GMRS divided by 1 plus GMRS, where RS is the resistance connected at the source terminal of the source follower. In this case, you have a current source connected at the source terminal of the source follower in parallel with a gate of this another transistor. So of course, both of them are infinite resistances. So your RS is actually infinity. If your RS is infinity, GMRS divided by 1 plus GMRS will be almost equal to 1. So your source follower will have a gain of 1. So at this point as well, you have the same voltage, I in divided by twice Gm. That will be the voltage at this point. On the other hand, this particular stage is again a common gate stage. Why am I calling it a common gate? Because as you see that the input is provided at the source. Input is provided at the source terminal. That's the AC input. Remember that this biasing transistor, a biasing source is just a current source. It's a DC current source that biases the transistor in saturation. The job of these DC current sources is to make sure that the transistor is biased in saturation. Also this V bias, the job of that is to make sure that the transistor is biased in saturation. Question?
What's the benefit of using current source for DC biasing rather than
So that's a great question, that why do we use the current source as the source, as the resistor? So one advantage is that ideally you'll have an infinite resistance. So your GMRS divided by 1 plus GMRS, the non-ideality comes in because RS is not infinite in the problems that we had seen before. But if you use a current source, then RS becomes infinite. So you do not see any kind of loss in the source follower stage, right? Your gain becomes 1. There are some other advantages as well for current-based biasing. One advantage of current-based biasing is that if you use a voltage, let's say I want to have a voltage provided at my gate, let's say V bias, either at the gate or the source or wherever you want to provide the bias. Now the problem with V bias is that at all these, at every terminal, there is some parasitic resistances. There is some parasitic capacitances, right? So parasitic capacitances and parasitic resistances will hurt the performance of the circuit. Why? Because there would always be some parasitic resistance, let's say, and then there would be some parasitic leakage current. So even if you're connecting this V bias to the gate also has some leakage in a real scenario. In a real MOSFET, the gate does not have zero leakage. It does not actually have infinite impedance because, as you know, infinite impedance doesn't exist. Right? It will always be some finite impedance. That means there is always going to be some finite current flowing through the gate. Right? Now, all these wires will have finite resistances as well. So as soon as you have wires that have finite resistances, and then you have a current, leakage current flowing through them, there would be a voltage drop across this resistor. So even though you wanted to apply V bias at the gate or at the source or whichever point you want to bias. So even though, let's say you want to apply V bias, what you're going to get is something that is a little lower than the V bias because of the voltage drop across the parasitic capacitance. Similarly, if you apply a V bias at the source over here, similar things will happen, that you're not going to get the same bias that you intended to because of all these leakage and parasitic components. So that is why you always in circuits, and we are going to learn about current mirrors in the later part of today's class as well as next lecture. That's where we'll learn that how to make sure that how do we create these current sources. That's what we're going to learn in the later part of the class. So that's why it's a very relevant question. Thank you for asking that. But why you are going to use current sources instead of voltage sources? is majorly because of this reason that if you use voltage sources, there would always be a voltage drop because of the parasitic resistance in the path or the wire resistance. However, if you use a current source for biasing, the same current will keep on flowing through that resistance, and then even at this node, although this is at a gate, so of course you cannot bias it like that. But for example, let's take the example here, that if you are biasing it using a current, even if there are parasitic resistances, the same current actually flows through the source. The same current actually flows through the drain. Right? Even though there are always parasitic series resistances because of wiring. That's why using current sources for biasing is something that is generally encouraged. You can also do voltage sources for biasing, but in that case, you have to be careful that there would always be a voltage drop, and you may not get the intended voltage at the intended point. If you're taking care of that during design, it's fine. But if you're using a current bias, then you don't even need to consider that, because current will the current that is flowing through your source or drain, that will always be the same current as your intended the current that is your intention in this case, right?
But
Okay.
regardless, we can still analyze the gain the same way as we do. Like using
Yes. Yes. Now, for the small signal model, again, you brought up an important point. Remember that this is DC bias. So for the small signal model, you don't even need to consider this, because DC and AC will keep separate, right? So DC is considered separately, AC is considered separately. So in the AC small signal model, this is just an open circuit. This does not even exist in the AC small signal model. And that is the reason why this entire current goes here, because this path doesn't even exist in the AC model. It's a DC source. And there is no, the impedance of that DC source is still infinite. All right. So again, consider the source follower and the gain of the source follower, consider the common gate stage and the gain of that common gate stage. And for the common gate, you'll get a gain of GM times R out. And for this particular R out, which is at this node, you'll see the R3 resistance, and you'll see another path, which is the gate of the N5 transistor, which is infinite resistance. So R3 in parallel with infinite, also you'll see another resistance looking down over here that is also infinite. So you'll see just the R3 resistance, which is 1 upon GM. So GM multiplied with 1 upon GM, because your R out is equal to 1 upon GM in this case, according to the problem that is given, because all the resistances are equal to 1 upon GM. That's what is given in the problem. So you have GM multiplied with 1 upon GM. So the gain of this common gate stage is also almost equal to 1. So whatever voltage that you generated here, you have the same voltage at this node, also at the same voltage at this node. Now, only the last thing to do is that you have these two common source stages. So this is a common source. This is also a common source. Again, the source is grounded. The input is applied at the gate. Here also the input is applied at the gate, and the output is taken at the drain. Only thing to consider is that the two drain nodes of M4 and M5 are connected together. M4 and M5, the drains are connected together. So how to solve this kind of problem? Again, remember that the transistor just converts your input voltage to an output current. So whatever input voltage that you had at this node and whatever input voltage that you had at this node, multiply with the GM of the transistor, you get the current at the drain node of M4 and the current at the drain node of M5. Now, because of KCL, those two currents add up. So what I just said is that, let me make this simple. The voltage at this node is equal to I in over twice GM. The voltage at this node is also, let's call that V4, and let's call this V5. This is also equal to I in over twice GM, as we have just solved. Now, these two voltages will generate a current through M4, and this will, the voltage V5, so this voltage is V5, and this voltage is V4. So V4 will generate a current I4 through M4's drain, and V5 will generate another current I5. What is going to be I4 and I5? So I4 is going to be equal to this voltage at the gate input multiplied with the GM of the transistor. So I4 is going to be I in divided by 2. That's it. And I5 is going to be equal to, again, I in divided by 2. Because I4 is equal to GM multiplied with V4 and I5 is equal to GM multiplied with V5. So you know I4 and I5, those two currents will add up and will flow through the resistance R4. And V out is nothing but R4, because again, looking into the drain of M4 and M5, you will see infinite resistance. That's why the output resistance at the V out node is equal to R4 multiplied, the resistance is just equal to R4, because the other resistances are infinity. The resistance looking into the drain is infinity. The resistance looking into the drain over here is also infinity. So you only see the R4 resistance multiplied with the current. What is the current? Current is I4 plus I5. And I4 plus I5 becomes I in over 2 plus I in over 2. That becomes I in. So R4 multiplied with I in, that is equal to your V out. And you are originally asked to find out what is V out as a function of I in. So you just found out that. Now you can also put the value of R4, which is 1 upon GM once again. So that's how we are going to solve this kind of a problem, that you divide and conquer. You already know all of these constructs. You already know this is a common gate. You already know this is a source follower. You already know this is another common gate. And you already know that these two are individual common source. So if I write those down, common source, this is a source follower, this is a common gate, and this is a common gate. So whenever you see a complex circuit, try to divide that into smaller parts and see what you are more familiar with. Right? And you'll see that there will be multiple components that you are already familiar with. Okay, any other questions on this? If not, let's look into the current meters for a bit. So current meter is going to be one of the key components in any integrated circuit. So whenever you have, let's say, tens or hundreds or even thousands of transistors, many of them will be used in the form of a current meter. Why current meters are required? Because let's again go back to this homework problem. How many current sources do you see here for biasing? You see one over here, you see the second one here, and you see the third one here. So now if you're going to implement this MOSFET as part of an IC, let's say you're building an integrated circuit, a chip. So you need to keep, let's say, 3 IO pads, or what does IO pads mean? That, okay, you have a chip, which is, let's say, 1 millimeter in width and 1 millimeter in height. So let's say you have built a chip like that. Now, let's say the chip contains this circuit. And these current sources, which could be the current sources that you see in your lab, those current sources need to be connected with the circuit somehow. So you need to have 3 different pads on the chip, and those pads will connect the external world with the circuits that are inside the chip. Let's say there are multiple transistors inside the chip, and you somehow want to connect to those transistors. So there are these 3 external pads. Of course, there's need to be a VDD pad and a ground pad as well. But these 3 external pads are going to be connected to 3 external current sources. That could be one way to do it. But that's a very bad way to design this circuit, because you'll need 3 external current sources. So your setup will be very complex again. So you'll have to borrow 3 current sources from the lab and do the testing, which is generally becomes a very cumbersome. Also at the same time, there could be mismatches between those current sources, and that will lead you to whatever I bias you wanted to have, I bias 1, I bias 2, or I bias 3. You might not end up with what you are intending, because there could be mismatches in those current sources. So what is generally done in an integrated circuit is that you generate one current source, or you take one current source from outside, and whatever other current sources you need, you generate them inside the chip. So that you only need to use one current source, and the current source 2 and 3, they are generated inside the chip as a function of that current source 1. And how that is done, that is called a current mirror circuit. So we are going to learn about what do we mean by a current mirror circuit. The current meter circuit looks like this. So let's first see how the circuit looks like, and then we'll analyze it. The job of the current meter is to copy bias currents around the IC and to implement active loads. We'll also learn what do we mean by active loads, but for now, let's just say that the job of the current meter is to copy the bias currents. You have only one bias current from the external world, and you're going to create the other bias currents using this circuit. So how does it work? You're going to use this as your external current source, for example, okay? And then put that current into the drain node of this first transistor M1, and you're going to connect the drain and the gate of that transistor together. You're also going to connect that same point to the gate of another transistor M2. Now, if you do that, and we'll now show the math that interestingly, whatever current that flows through this transistor M2 will be exactly equal to the current that was flowing through the transistor M1 if the size of the transistor M1 is equal to the size of the transistor M2. And by size here, I mean the aspect ratio, that is the W/L ratios of the transistor. So now let's see the math to understand why it happens like that. So the assumption here that the M1 and M2, these transistors are matching transistors. That means they're designed in the same IC process and their parameters are identical. Let's say that the threshold voltages are identical, VT1 equal to VT2 equal to VT, and K1 prime equal to K2 prime, that is equal to mu times COX equal to K prime. Let's just assume that those are equal. The K primes, the process transconductance are equal, and also the threshold voltages are equal. Although that might not happen in a real scenario. Right? There might be a small difference, but that's again too complex to analyze right now because we are learning this circuit for the first time. So we'll assume that the threshold voltages are equal, and we'll also assume that the K parameters, the device transconductance parameters, are also equal. Now, the way the M1 transistor is connected, that is called a diode connected transistor. If you connect the drain and gate together, then that transistor is called a diode connected transistor, and that becomes automatically, that goes in the active region or in the saturation region. Now the question is, why is that? There are two questions. That why would you call it a diode connected transistor? And the second question is, why is it automatically in the saturation or the active region? So let's just try to understand first, why are you going to call this a diode connected transistor? So you have the transistor, you connect the gate and drain together. So this is your source, this is the drain, and this is the gate. So as you know that for the diode, the current only flows in one direction. So the current flows in this direction, but the current cannot flow in that direction. The same thing happens for the diode connected transistor. So if you're already connecting the gate terminal and this terminal, so the transistor, let's say it has 3 terminals, neglecting the body terminal for now. You have 3 terminals, you're connecting the gate with another terminal over here. And in that case, if the drain terminal is at a positive potential, if this is positive potential and this is negative potential or ground, the current flows from the drain to source, which generally happens in a transistor as well. The only thing that you need to take into account is that the VGS, the gate to source, has to be higher than the threshold voltage. The gate to source voltage has to be higher than the threshold voltage, so the transistor will be on. The other condition for saturation or active region for the MOSFET is what? Your VDS needs to be higher than the overdrive voltage. VDS needs to be higher than overdrive voltage. Now, what is the in this case, because your drain and source are connected together, your VDS is equal to your VGS. So your drain to source voltage is equal to your gate to source voltage because drain and gate are connected together, physically connected together. What is your V overdrive? V overdrive is defined as VGS minus VT, right? V overdrive is VGS minus VT. So your VDS is equal to VGS and your V overdrive is equal to VGS minus VT. Your VGS is always going to be higher than VGS minus VT for the NMOS. And that is the reason why this transistor is always in saturation. Only thing you need to ensure is that your VGS is higher than the threshold voltage and the transistor will always be in saturation. You don't even need to think about it. You don't even need to analyze and figure out whether your VDS is greater than V over drive or not, because it is going to be, your VDS is going to be higher than your V over drive. Just because your VDS is equal to your VGS and V over drive is equal to VGS minus VT, and VGS is always going to be higher than VGS minus VT. Okay. So a diode connected transistor is always going to be in saturation. Now the question is something that we still didn't answer, that why are we calling this diode connected? Now imagine that you reverse the polarity of the positive and the negative voltages. If you reverse the polarity of the positive and negative voltages, let me just clear this part, right? So, because these are all known equations that we had written, and these equations explain that why the diode connected transistor is always in saturation. Now, let's say I put a positive voltage on the source side, or basically on this terminal, and a negative voltage on the top terminal. Now, because as you know that for, oops, sorry, let me draw this again. So you have a positive voltage in the bottom terminal, and you have a negative voltage on the top terminal. Now you know that for a MOSFET, whichever terminal is at a higher voltage, that will be the drain terminal, because the current flows from drain to source for an NMOS, N-type MOSFET. The current cannot flow from source to drain, because electrons flow from source to drain, and electrons flow in the opposite direction of the current. The source is always the source of the majority carrier. That means the source is always the source of the electrons in this case. That means electrons are always going to flow from source to drain. That means current is always going to flow from drain to source. So as soon as you put a positive voltage on the bottom terminal over here and a negative voltage on the top terminal, the bottom terminal becomes the drain and the top terminal becomes the source. Because that has to be the case. The source terminal has to be at a lower terminal than the drain terminal, because by definition, because electrons will flow from source to drain. That means current will flow from source to drain to source. That means this arrow will be over here now. Okay. Now what do you have for the transistor? Your gate and source are connected. If your gate and source are connected, your VGS is less than your threshold voltage. VGS is 0. So until and unless your threshold voltage is also 0, the transistor can never be on. And that is the reason why we call it diode connected, that current only flows in one direction. If you are having positive voltage here on the left side of the diode and negative voltage on the right side of the diode, then only current flows. As soon as you reverse the polarities of the voltages, you put positive voltage on the right side and negative voltage on the left side, current cannot flow. The same thing is happening with the diode connected transistor, that if and only if the top terminal is positive and bottom terminal is negative, if the top terminal is positive and it is the drain and the bottom terminal is negative, it is the source, current only flows in that case and current cannot flow in the other scenario. And that is the reason why we call this a diode connected transistor. Okay. All right. Now, for this diode connected transistor, it is automatically in the active region. It will always be in the active region, as we just explained, because VDS is equal to VGS and V overdrive is equal to VGS minus VT. So your VDS is always going to be higher than V overdrive. That means the transistor is always going to be in the active region. Now VGS2, the gate to source voltage of transistor M2, that is going to be equal to the gate to source voltage of transistor M1. Why? Because the gates are connected together and the sources are connected to ground, which means they are also connected together. So the VGS of the second transistor is equal to the VGS of the first transistor. And VGS of the first transistor is equal to VT plus V overdrive, just by definition. And V overdrive is square root twice ID over K. That's the formula you have used in your homework 4 and homework 5. So VT plus square root of twice I divided by K1. And what is the I? This is the I1. The I1 current that is flowing through the M1 transistor. So VGS2 is equal to VGS1. VGS1 is equal to VT plus V overdrive of 1. And V overdrive of 1 is square root of twice I1 over K1. So now you know that your V overdrive of 2 is equal to your V overdrive of 1, because VGS2 was equal to your VGS1 and VGS1 is equal to VT plus V over drive. Because the VTs are equal, the VT for transistor M2 is equal to the VT for transistor M1. That means the V over drive for transistor M2 is also equal to the V over drive of transistor M1. Right? Otherwise, this cannot be true. That VGS2 is equal to VGS1, which is equal to VT plus V over drive of 1, which is also equal to VT plus V over drive of 2. That means V over drive of 2 has to be equal to V over drive of 1. And if so, V over drive of 1 is equal to square root of twice I1 over K1, and V over drive 2 is equal to square root of twice I2 over K2. Now, if K1 is equal to K2, that is the device transconductances are equal. If K1 is equal to K2, then I1 has to be equal to I2. Which means that whatever current was flowing through the transistor M1 has to be the same current that flows through the transistor M2. But there is only one single catch over here, that we just assume that K1 is equal to K2. But in the assumption, it was K1 prime equal to K2 prime. So what is the difference between K1 prime and K2 prime and K1 and K2? Is that K1 is equal to K1 prime times W over L of 1. So the width and length of 1 multiplied with K1 prime, that gives you K1. And K2 is equal to K2 prime times W over L of 2. So if the width and lengths of transistor 1 and transistor 2 are equal, then the currents I1 and I2 has to be exactly equal. If they're not same, if the W over L ratios are not same, so in that case, you just have this expanded version that your I2, which is K2 over 2 times V over drive squared, which is equal to K2 over 2 times V over drive 1 squared. Now you just expand that, and then you'll find out, we'll go through this in detail in the next lecture, but you'll see that I2 over I1, the ratio of the currents I2 and I1, will be a ratio of the W over L of the transistors M2 and M1. So depending on the W over L ratios of the transistors, you can figure out what is going to be your I1 and what is going to be your I2 as a function of your I1. So you cannot only mirror it, that I2 equal to I1, that's very easy. If your W over L ratios are same, then I2 will become I1. If the W over L ratio of the transistor M2 is 2 times that of the W over L ratio of transistor M1, then the current through M2 will be double of the current through I1. So it can be a ratiometric calculation that I2 over I1 is going to be the ratios of W over L for transistor M2 and M1. So we'll go through this derivation again in the next class, because I don't think we got enough time, but let's continue from here on Wednesday's lecture.